Good evening, everybody. Welcome to Mexborough and Swinton this evening. I'm introducing Professor Andrew Coates. He gained a Bachelor of Science in Physics from UMIST in 1978 and a Master of Science in 1979 and a Doctorate of Philosophy in 1982 in Plasma Physics from Oxford University. He's been at the UCL's Mullard Space Science Laboratory since 1982 with temporary guest positions at the Max Planck Institute for Solar System Physics in Germany, the University of Delaware in America, and the BBC World Service Media Fellowship. He is now Deputy Director for the Solar System at UCL MSSL. Space mission involvements include the Rosalind Franklin ExoMars in 2022 rover, where he leads the Pancam team, Cassini, where he leads the electron spectrometer team, part of the Cassini plasma spectrometer, Venus Express, Mars Express, and Giotto. Science interests include the solar wind interaction with planets and comets, and space instrumentation. He has authored and co-authored over 530 publications, including over 430 refereed. He is currently a member of STFC Science Board, and he is an active in space and science outreach, and is incoming president of the Society for Popular Astronomy. So if you please put your hands up and welcome Professor Andrew Coates. Thank you.
Thank you very much. Good to see everybody. Thank you. And thank you for the nice introduction. So I'm just want to check that you can see that in full screen, can you? Okay, so yes, I'm going to talk to you about looking for life on Mars. So I'm at Mullard Space Science Lab, University College London. So we're not in London. We're out in a country location, Holmbury St Mary, which is in the Surrey Hills, a little bit outside of Guildford. So about 35 miles out of London, south of London. We do space science research there. So we have about 200 people working on space science and instrumentation, and it's scientists and engineers, and actually scientists and engineers working together. This is what we do to build instruments for international missions and go off and measure things. So one of the things is we built what we can see on the right-hand side here, the camera system, which is on top of the mast of the ExoMars 2020 rover, also called Rosalind Franklin, and we'll go into that later. So I'll tell you a little bit about what we're interested in doing. So we're looking at Mars 3.8 billion years ago and Mars now, a bit about water and a bit about life, and then about the ExoMars Rosalind Franklin rover. And this is our website here. This is our Twitter. I don't know if people use Twitter there or not, but and we've acknowledged the funding from the UK Space Agency for us to help us to build the instrument. And this is our logo of Pancam. That's the panoramic camera system. That's what Pancam is short for. Okay, so I will start by looking for the different locations for life beyond Earth. So these are the possibilities which have come up in the last few years, some of them very recently. Mars, of course, you know, people for a long time have wondered about the possibility of life on Mars, about whether there could have been life on Mars, because conditions on Mars used to be very different to the way they are now. And there's the possibility for life having developed there around about the same time as it developed on Earth. So Mars is about half the size of the Earth, and that's important for some things we'll talk about later. So that meant it loses its heat of formation at the beginning of the solar system 4.6 billion years ago. That's when the solar system began, from the swirling cloud of gas and dust. So Mars gradually lost its heat as Earth did, but Mars does it more quickly because the Earth is bigger, and the amount of heat you lose is proportional to the area divided by the volume. So that means it goes off as 1 over the radius. So for a smaller body, it loses its heat more quickly. So Earth didn't lose its heat more quickly, and so it still has a relatively warm interior. Okay, so Mars is one of the top locations to look for life on Earth, life beyond Earth. Europa is another one, so one of the moons of Jupiter. So this is an icy crust here, and underneath the icy crust there is a liquid water ocean, slightly salty, but according to magnetometer measurements and gravity measurements which have been made there seems to be a liquid water ocean underneath an icy crust. And so that is in Jupiter's system, quite close, you know, obviously it's one of the Galilean satellites, relatively close, orbiting relatively close to Jupiter. So it's bathed on the surface by radiation from Jupiter's radiation belts, but underneath it has water underneath this icy crust. And so the possibility is that there could perhaps be life there. There seem to be the ingredients for life, and we'll go into that a little bit more later as well. On the top right, and I should say Europa is about a quarter of the size of the Earth, so smaller, of course, than Mars. Enceladus is about 1/25th the size of the Earth. And Enceladus, the Cassini mission, which went to Saturn, arrived at Saturn in 2004, made measurements until it burnt up in the atmosphere of Saturn just a few years ago. So one of the things it discovered was plumes of water coming out from the south pole of Enceladus. And that is from a subsurface ocean as well. So from the Cassini mission, we discovered that there's a water ocean underneath the surface of Enceladus also. And it turns out the ingredients for life are there as well, including hydrogen, which was discovered relatively recently by the iron and neutral mass spectrometer. That's one of the things, in addition to carbon, hydrogen, nitrogen, phosphorus and sulfur. Those are the things which you need for life. And so Enceladus is another place where perhaps there could be life even now. So Enceladus and Europa, there could perhaps be life now, even primitive type of life, maybe in these subsurface oceans. But Mars, we think it's past life 3.8 billion years ago, if it happened there. Okay, another image here is Titan. So this is another moon of Saturn, orbiting a lot further from the planet than Enceladus is, at about 20 Saturn radii. And of course, you can see that through telescope and binoculars and things like that. And that is interesting. It's 25-75 kilometers, so a little bit smaller than Mars. But nevertheless, it's the second largest moon in the solar system. And it's the only moon in the solar system which has a significant atmosphere. So the haze which you see here is to do with its nitrogen and methane atmosphere. And so you get this, this haze. Actually, these pictures are a combination of ultraviolet and visible pictures. This picture at the bottom of Titan, so you can see through to the surface. But when Voyager first passed Titan in 1979, it showed that, I mean, it took visible cameras, and the images which it got were orange, hazy type of object. So you have to go into the ultraviolet and indeed infrared in order to peer below those clouds at Titan. But we think Titan also has a subsurface ocean underneath its very cold surface. Its surface is 94 Kelvin, so minus 270, minus 180 degrees, something like that. And so that means that we have a very cold surface. It's cold enough that basically there seem to be cycles involving methane. So methane plays the same role that water does on Earth. So we of course have rain only too often in the winter and so on here, and that's water of course on the Earth. But on Titan, it's raining methane and ethane and things like that. So it's things which are, you know, are at their triple point. In fact, methane's triple point is at 94 Kelvin. And so that temperature means that you can have methane in the atmosphere. Methane lakes. So we have lakes on the surface, and there's also in the gaseous state as well in the atmosphere. So we can have water, a weather cycle at Titan involving water. So very interesting, but we think it's too cold there for life to be there now, probably even in the subsurface ocean, although some people would like that, think that might be the case, but this is sort of speculation. Okay, so another bit of speculation recently with Venus and the detection recently of phosphine in the atmosphere of Venus. So of course that has got that phosphorus in it, one of the ingredients for life. And so this was a very exciting discovery by Jane Greaves and colleagues at Cardiff, and they discovered that there's phosphine in the air, in regions of the clouds of Venus. So regions of the clouds of Venus, basically sulfuric acid clouds, but it turns out there's phosphine there as well. And there's a big debate in the scientific community about whether there might or might not be life there even. So these are the top places where life could have developed, or could even be there now in these cases, Enceladus and Europa in the solar system. But at the moment, we have no proof. The only proof we have for life is on Earth. And so obviously we're here, we're able to use Zoom and talk to each other and things like that. So Mars is one of the top locations for looking for life on Earth, and hence the interest in Mars. These other objects, there will be missions in the future. So the European Space Agency has the JUICE mission, which is going late next year. We hope the launch is now. That gets to the Jupiter system in the early 2030s and then goes into orbit around Ganymede after doing some flybys of Europa and Callisto on the way, and then it goes into orbit around Ganymede, which is the only moon with a magnetic field. So a very exciting mission, and that will be going to Europa. Of course, NASA has missions going to Europa as well, the Europa Clipper, which will do flybys of Europa. That will be interesting. In future, there will be, I'm sure, returns to Enceladus and Titan, and in fact, definitely with Titan, that's the case. There's a helicopter or quadcopter going to Titan, Dragonfly, going in the late 2020s. This is in addition to the Mars helicopter, which is going to be doing its testing in the next week or so. So that'll be very exciting. And then future missions to Venus, I'm sure, will happen as well, and partly associated with this recent result. Okay, so these are places in the solar system where there could either be or there could have been life, but Mars is one of the favorites. Of course, it's the closest, easiest to get to, and we think it is going to be, evidence from there, probably, which tells us about life beyond Earth. Okay, so the next slide tells us how Mars has changed. So 3.8 billion years ago, so remember, solar system started 4.6 billion years ago. So this is a long time ago in Mars's history. 3.8 billion years ago, Mars had water on the surface. And so there's lots of evidence for that, starting with the Viking missions in the 1970s. This particular image is from Mars Express, the European Space Agency's Mars Express mission. It's a 3D image, so it's showing one of the ancient river channels. Water, there used to be water on the surface of Mars. Now there is not. It's a much colder and much more hostile environment for water or life or anything else, as we'll see a little bit later. But 3.8 billion years ago, it had water on the surface. Mars also at that time had a magnetic field. And there's evidence for that from this mission called Mars Global Surveyor. So here we're plotting latitude and longitude. It's basically a map of Mars, and the color scale here is giving us the altitude on Mars surface, the altitude of features on the Mars surface. So we can see it's very low in the northern hemisphere of Mars, very high in the southern hemisphere. In fact, these are the southern highlands. And actually the crater count is higher here as well. The cratering density is high, and this means that that surface is about 3.8 billion years old. The height actually goes from white are the very highest peaks here. So the volcanoes, Olympus Mons and the Tharsis volcanoes here, going down through the lower regions to the sort of polar regions and to the Hellas Basin, which are the lowest points on Mars. So that's the color scale. And what's shown on the top of that is measurements that were taken when the first magnetometer was taken close to the Mars surface, or close enough, a few hundred kilometers above the surface on Mars Global Surveyor. That's the first time that had been done, and so that showed that there were crustal magnetic fields, and that's shown by these black and white contours over the map here. And so that's where Mars Global Surveyor actually detected a magnetic field. So the white indications, contours, are magnetic field which is pointing out, and then black ones are the field pointing in. You can see this is a sort of cusp-like configuration. So this is a bit like a bar magnet just underneath the surface or something like that. That would do that with iron filings. For those of you that might remember that experiment being done at school, iron filings showing a magnetic field. So this is using magnetometer measurements, but it's doing the same sort of thing of being able to look at to look at the magnetic field. So we have regions of magnetic field here. They're all in the southern hemisphere, and they're crustal magnetic fields. So this is not a global magnetic field like the Earth has. But it's a crustal magnetic field. So there's a magnetic field in the crust, and that is a remnant of a time when Mars used to have its own global magnetic field like the Earth has now. But that suddenly stopped about 3.8 billion years ago, probably due to cooling, so that Mars' surface being able to cool more quickly, and the volume of Mars being able to cool more quickly than the Earth at the beginning of the solar system. That means that the iron core probably froze up, and so the magnetic field was then lost. But the magnetic field was trapped in the forming rocks in these old regions of the Martian surface, and so we get those crustal magnetic fields being seen there. Okay, the third bit of evidence for Mars being much more active 3.8 billion years ago than it is now is volcanism. And so this is a picture of Olympus Mons, the biggest volcano in the solar system. So on the map of Mars here, it's this object here. And then this is about 600 kilometers across. It's a shield volcano, so it's a bit like the Hawaiian Islands on Earth. But the height of this is about 27 kilometers high, so it's about 3 times the height of Mount Everest compared to the surrounding terrain. So it's a very large volcano. So volcanism was going on as part of the cycle which was going on involving water, the evidence for that on the surface there. The magnetic field was there, helping to keep the atmosphere in. And so this time, 3.8 billion years ago, Mars had water, it had a magnetic field, and it had volcanism. And we think that life could have started on Mars at that time. So that's why 3.8 billion years ago is a key to 4 billion years ago is a key time on Mars. Mars now, very different. So it has extinct volcanoes. There's no active volcanism at the moment. There's no large-scale magnetic field. There's only these crustal or remnant regions of magnetic field. We have a very thin atmosphere. It's only 7 millibars. It's a carbon dioxide rich atmosphere. It's cold and dry. And this is an image from one of the earlier rovers, the first rover which was able to actually land on Mars. And it really is cold. On a daytime on Mars near the equator, it'd be something like 0 to 20 degrees centigrade, something like that. But at night, down to minus 90 to minus 120 degrees centigrade. So very, very cold at night. The day on Mars is just over the 24 hours. It's 24 hours, 40 minutes, just under on Mars. So just a little bit different to our day length. So every day and every night, that temperature swing goes from 0 to 20 down to minus 90 to minus 120. So anything we put on the surface of Mars has to survive that temperature range. And so that's one of the big engineering challenges of sending things to Mars, and something which we have to cope with the rovers. So Mars now very different to the way it was. Okay, so we know that there used to be water on Mars. So where did it go? So some of it we think went underneath the surface. And there's some evidence for this, which has been building up with the rover missions, starting off with Spirit and Opportunity, but then going on to Phoenix in 2008, which basically took, this was a static lander rather than a rover, and it took this sort of digger thing along to be able to move material from the surface. And so on the right-hand side, we see what that scoop has pulled away. It's just a few centimeters underneath the surface. And there are two images being superimposed, one on top of the other here. So there's from the initial scoop, there's something there. And then a few days later, when this image was taken again with the same lighting conditions, those things have gone. So what's happened is that is water ice, which is just underneath the surface near the pole where Phoenix landed. And so that sublimes into the atmosphere. It goes straight from the solid state into the gaseous state or vapor state. And then so it disappears basically. So we see now you see it, now you don't with the water ice. And so that's why that thing is flashing there. So that gives you a sign that there's water ice just underneath the surface in this location. In fact, there have been many missions now looking at water. So one of those was Mars Odyssey, which was able to use neutrons to map out hydrogen underneath the surface, which was thought to be linked with water. And so that finds 3 locations on the equator, which there's a reasonable amount of water underneath the surface, and some polar regions as well. And so that and recent missions also, which I'll talk about later. Okay, in fact, one of the more recent missions is Curiosity, the Curiosity mission, which is on the surface of Mars now, still doing its work. So with that, evidence for an ancient lake and stream deposits were found in this particular location in a paper in 2014. And not only was there a lake, which was the inference was from doing chemical analysis from drilling just underneath the surface, that water must have been involved here for quite a long time. This scale bar here at the bottom is 25 kilometers. And so, so this whole lake is maybe 50 kilometers and maybe 20 kilometers wide or something like that. And so that's the suggested size of a lake on Mars. And not only was it a lake with water in it for a certain time, it also had the right acidity, the right pH for microbial life. It's not the discovery of life, but it's the discovery of the right type of water to potentially harbor life at that time, very ancient time, 3.8 to 4 billion years ago on Mars. So there's a lot of evidence, which there isn't time to go through all of it, but this is some of the evidence which has been building up for water on Mars. More recently, even, the European Space Agency's Mars Express mission, that had a radar sounder on board called MSAS. And one of the things which was done with that was to look underneath the surface near to the South Polar Cap. And so this is the South Polar Cap on Mars. Just near that, this is a region under the surface where the radar echoes changed in such a way that it was consistent with liquid water being under the surface, maybe about 1.5 kilometers underneath the surface. Perhaps this lake is about 4 kilometers wide, so more water being trapped underneath the surface of Mars. So some of the water which was originally on Mars, some of it has gone underneath the surface, and some of it also has escaped. Actually, this is a bit more about the water which was under the surface. So more recently, in September last year, some more was done about this region in the South Pole. So again, some more mapping with that MSAS radar with a bit more detail about these lakes. And so a couple more lakes, or 3 more lakes, were found in that Nature Astronomy paper. So again, some of the water has gone underneath the surface of Mars. So some of it has also been pulled away by the solar wind. So people may be familiar with the solar wind. So this is a 1 million ton per second stream of material coming out of the sun all the time. It's in the plasma state, so beyond the states of solid, liquid, and gas. So this is plasma. The 4th state of matter is basically ionized gas. So you have electrons and ions moving together out away from the sun. And it's a very highly conducting, it's very high conductivity, and so it carries the magnetic field out actually with the flow of plasma away from the sun. But the particles and magnetic field then interact with the different objects in the solar system. So on the left-hand side here, we see the magnetized objects, the objects with a magnetic field, so like the Earth. So, of course, we know the Earth has a magnetic field. We used to use compasses for navigation. and homing pigeons and still like that, things like that do actually still use magnetism for steering. On Mercury, there's a magnetic field as well, much smaller and much less, less large in space than the Earth, and so it's in this little box here on the scale of the Earth, but it has a magnetic field, which was a surprise. Bepi Colombo, that mission is on its way to Mercury to understand more about that and how it forms. On the larger scale, we have Uranus and Neptune. These are really exciting objects, which Uranus in particular, the spin axis is in the ecliptic plane, and the magnetic axis is a large angle to that. So the aurora on Uranus would move round and round. And actually, some of our team had a paper published just yesterday about X-ray observations of the aurora on Uranus, and so that's quite fun for people that are interested in current science. Okay, so Neptune also has an interesting magnetic field as well, and so we hope that there will be a mission to these outer ice giants sometime in the next 10-20 years. So we're working towards that at the moment in the community. On the larger scale still, there's Saturn and Jupiter. Jupiter, if you could see Jupiter's magnetosphere in the sky, it would be larger than the size of the sun or the full moon, so absolutely enormous. And but basically all of these objects are magnetized. So that magnetization is important in the interaction with the solar wind, because the solar wind, as I said, is a magnetized plasma, so they're charged particles. And so if you have a magnetic field, a strong one like the Earth, that can deflect the solar wind. You get a bow shock upstream of the magnetic obstacle. It's pushed in on the day side and then pulled out into a tail on the night side of the Earth's magnetosphere. And so this helps to protect our atmosphere from being stripped away by the solar wind. So objects without a magnetic field aren't quite so lucky. So Venus, Mars, Pluto, and comets, none of those have magnetic fields at all. And so Venus is unmagnetized. Mars is unmagnetized now, except it has those crustal magnetic fields. Pluto, no magnetic field. Comets, no magnetic fields. And so comets, you can see, of course, in the night sky, you can see comets every now and then, which can be very spectacular, as I'm sure a lot of you have observed comets. The other visible thing about this field, of course, is the Earth's aurora. We can see the aurora, the northern and southern lights. I'm sure you sometimes get that up there infrequently, but I'm sure some of you will have seen that, or in northern Scotland, or in northern Scandinavia, northern Canada, and indeed in the Antarctic as well. So those are possible places to see the aurora on Earth. All of that breathing with the solar wind and changing with the solar wind as that changes. But the solar wind can get to the top of the Mars atmosphere, and the same with Venus, Pluto, and comets. And so with comets, you get these tails. So there's a dust tail, there's also a plasma tail or iron tail. That's to do with the solar wind interaction. We were able to look at that with the Giotto mission to Halley's Comet, and also Grigg-Skellerup, and of course more recently with Rosetta, and in the future with Comet Interceptor. And so comets are very interesting objects to study and their interactions with the solar wind. But Mars is an object with an atmosphere. I've said it's a thin atmosphere, less than 1% of the Earth's atmospheric pressure. And Mars's atmosphere can be stripped away. So what we think happened is about 3.8 billion years ago, Mars's magnetic field just stopped. And so since then, the solar wind has been scavenging away the atmosphere of Mars. It happens at Venus as well, but that is pumped up, was pumped up by volcanoes, and may still be being pumped up by volcanoes as well. That's one of the strands of evidence for that. And Venus, in fact, having a very strong and a high-pressure atmosphere, much higher than Mars's atmospheric pressure. Okay, so the solar wind interaction with these objects is important, and so the solar wind may have stripped some of the water from Mars away. So you've got some water going underneath the surface, and you've got other water escaping to space via this interaction with the solar wind. And so this is something we also study in our research group. And there's an artist's illustration of this, showing not to scale, the sun in the middle of the solar system there. This was Mars. This is an illustration for the MAVEN mission, which was done a few years ago. And so that shows how these plasma particles stream away from the sun in all directions all the time. That, of course, is currently being looked at by the Solar Orbiter mission, which is very exciting, another European Space Agency mission. But escape from Mars is what we're interested in. So we can measure the escape from Mars now and project that back over 3.8 billion years and come up with the conclusion that Mars probably had, maybe 100 meters of water, up to 100 meters of water equivalent associated with the planet. So as I say, some of that original water has gone underneath the surface of Mars and some of it has escaped. And so we can start to quantify that with the missions which are going on now. But the solar wind has played a role. Okay, so Mars has changed. So 3.8 billion years ago, it might have been something like on the left, which looks, to all intents and purposes, a bit like a signature of Earth now. But 3.8 billion years ago, Mars might have looked similar, with continents, an ocean, clouds here in the atmosphere. We know it had a thick atmosphere. We know it had water on the surface, and it may even have looked like this. And this is about the same time life was developing on Earth, as I said, and so that's why we think that life could have developed there. And we think it's not there now because Mars now is much harsher. The surface is very harsh with that very low temperature, as I said, but also because of the thin atmosphere, it means that ultraviolet from the sun can get through the atmosphere and bathe the surface, so anything would be zapped. It's a bit like being under an ozone hole all the time on Mars. It's also bathed in cosmic radiation. So this is radiation from the sun and from the galaxy. So that radiation can get underneath the surface. So we had a student, worked with a student a few years ago to look at how deep you have to drill underneath the surface of Mars for something to maybe survive. And the answer is about 1.5 meters. And so with Rosalind Franklin, we're drilling 2 meters underneath the surface. And so that's why we're drilling so deep. Okay, so this question of life on Mars. So was there life on Mars? So it's a possibility. When Mars was warmer and wetter, about 3.8 billion years ago. So a lot of people might now find some evidence which was announced in 1996 from this meteorite, Allen Hills 84001, which was picked up in Antarctica. So some scanning electron microscope images showed things like this, but this is, most of the community find that unconvincing now, that it actually was terrestrial contamination associated with this thing coming through the atmosphere. So we don't think it's life from Mars, which has come in this meteorite. So we have to go to Mars to find out. And so these missions are really aimed to look at that. So what do we need for life? So I've mentioned water quite a lot. So liquid water, of course, is something which we need for life on Earth as we know it. So this picture on the right is the early Mars, but it looks a little bit like Earth now. We need these essential elements, so carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. We need a source of heat to drive the right chemical reactions, and we need enough time for life to develop. So we think all of those things were there on Mars. We believe, based on measurements, that they're there at Europa and Enceladus as well. So those are interesting places to look to, as I mentioned at the start. So we think all of these, the only question is, was there enough time for life to develop on all of these, like any or all of these objects? Because at the moment, we only know of life on Earth, as I said. But early Mars is a possibility. Okay, so Mars Express was launched in 2003. It got there in 2004. And one of the things this was doing was looking for water in a number of different ways. So I mentioned MSAS, the antenna, which looked underneath the surface and found those lakes underneath the South Pole. So that's one of its major contributions. And it is able to basically bounce radar off the surface and subsurface regions to probe the subsurface regions and look for signs of ice and water underneath the surface. We can also look with Mars Express for water in the atmosphere, and we can look at water escaping to space as well. So there's a little instrument on here called Aspera 3, which we were involved in. So I have a student still working on the data of that, which is very good. So Catherine hopefully will be, well, she's a first year student at the moment, so hopefully we'll find some really interesting results out during her research project. Mars Express also took Beagle 2. So Beagle 2 is shown on the top here. So this was the UK's attempt to land on Mars. It did land on Mars successfully, as we found out several years later. We provided the camera systems for this, and this is what got me into actually looking at surfaces on planets, and developing the technology to be able to do that. But unfortunately, Beagle didn't send any data back to Earth. It did land successfully, apparently, but it didn't send any data back to Earth, which was a real shame. And of course, Colin Pillinger was the founder of that project, and you know, the prime mover associated with it. And it's a shame that he didn't even know, because he sadly passed away before we knew that Mars Express had been found on the surface by the Mars Reconnaissance, Beagle 2 had been found on the surface by the Mars Reconnaissance Orbiter. So we had high hopes for Beagle, and now we have this another mission going in next year now. Okay, so one of the exciting results from Mars Express was the discovery of methane on Mars. And so it found trace concentrations of methane, which is only 11.5 parts per billion. So this is Vittorio Formizano, a paper in 2004. And this confirmed telescope observations, which were done around about the same time. It's a controversial result because it's a very difficult thing to see in the data, but they believe they did see it. And why is it interesting? Methane should be very short-lived in the Martian atmosphere, only hundreds of years perhaps, because it is in the sunlight, and the sunlight, as I say, can get through the atmosphere of Mars very well, the ultraviolet in particular. Methane should be ripped apart relatively quickly. So this means there must be a source, a relatively recent source of methane on Mars, which we haven't expected. So there must be a source now. And there's two possible sources. One is geothermal activity. The other one is life. You know, either of those would be amazing. We had thought that Mars was basically didn't have geothermal activity going on now, but of course, if it has life going on, that would be really exciting. And these would be things like methanogens, a bit like you get in swamps, very primitive type of life. But we don't know if this methane is to do with life or not. They're very tantalizing results. So the Curiosity rover, which I mentioned is on Mars now, that has an instrument called SAM on board. So this measures, as well as stuff associated with surface samples, it measures bits of atmosphere as well, you know, samples of atmosphere. It looks for methane. And so early on, they first didn't see any methane at all. So they thought, oh, this is not there. And then in 2014, there was a spike of methane. In 2018, there was another one. And in fact, Mars Express saw that methane at the same time. So what we now think is that methane actually is a seasonal thing on Mars, and it probably happens quite close to the surface. We're trying to understand the process because there's another spacecraft which is trying to look for that, which hasn't actually found it yet, but it's probably to do with needing to be very close to the surface. Also, oxygen was recently detected in small quantities. Molecular oxygen was recently detected with Curiosity as well. So that's another interesting result, and one of those things in what you need for life. Okay, so about future missions to Mars. So missions to Mars, so European Space Agency and Russia, we are working together on two missions, looking for signs of that methane that was launched in 2016 and got there in 2017. It got into its science orbit in 2019, and since then it's been hunting for methane as well as other trace gases. It's found other trace gases, and it's found interesting information about the water cycle, but it has not found methane yet. And so that probably is because there are processes going on which we still don't understand, which is keeping that methane close to the surface. So that's one of the missions, the European Space Agency and Russia working together. The other one is the ExoMars Rover, shown on the right here, launching in 2022. So that's next year. It's actually next September, 21st of September next year. And so this is the rover on the surface of Mars. And so this is our camera system, Pancam. So this sits 2 meters above the surface of Mars on the top of this mast. So here's the rover. is what they call the bathtub, which contains some of the instruments. It looks a bit like a bathtub, but it's filled with electronics and instruments. This is the sample drawer on the front here, and this black thing on the front is the drill. So that is the thing which allows us to drill up to 2 meters underneath the surface. That comes in 4 stages, and so you add a drill and then drill down. And we're taking some spares in as well, just in case a drill breaks. So here's the wheels of the rover. I'll show you a little bit more about the rover later on. This is the landed platform. This is called Kazachok. So this is after the Russian dance. So that will dance through the atmosphere as it descends and hopefully land on the surface correctly. And the rover will drive off the ramps to look for signs of life. So it drills underneath the surface and gets samples and looks for life. So NASA, of course, are active at Mars as well, and right at the moment, InSight is still on the surface and making measurements. Its seismometer is working very well. There's UK involvement in that, so there's some very interesting data from that showing Mars quakes. So this is what happens when a meteor hits the surface of Mars. The surface rings like a bell, a very quiet bell, but nevertheless it rings a bit, and so you can detect that with sensitive seismometers. There's also, of course, the Perseverance rover. So that was launched in 2020 and landed in February successfully. We have a small involvement in that as well, in the MASCAM Z instrument, which is a little bit like our PamCam system, and taking amazing images on the surface of Mars. This year is a very busy one at Mars. So in February also, the UAE's mission, HOPE, that arrived successfully, having been launched in 2020. Also, the Chinese have a mission, Tianwen-1, that was launched last year as well, arrived successfully in February, and it has a rover which will actually try to land in May. So we understand that is May when that will try to land on the surface. So Mars is very busy this year with 3 missions, and so but our mission is the only one going next year. That's the one launching in 2022. And that will be, as I say, going straight to the heart of the question: was there life on Mars? Perseverance, by the way, is going to, as well as looking for evidence of life on Mars itself, that will collect samples in metal tubes ready for being brought back to Mars. So a Mars sample return, which is another pair of missions which will go hopefully in 2026 and 2028. It's not approved yet, but that's the hope. And so these samples which Perseverance will gather can be brought back to Earth for the very sensitive labs on Earth to be able to have a look at those samples and to look again for traces of biomarkers on life. But we're looking directly for biomarkers with ExoMars. Okay, and this is the instruments on the ExoMars rover. So on the left-hand side, these are the instruments which get context. In the middle is the drill instrument. On the right-hand side are the analytical drawer instruments. And so the context ones are things like our Pancam cameras. So you can see this has got a UK flag on it. That's because we're leading this collaboration. We're the only, so I'm the principal investigator for this instrument. We involve Germany, Switzerland, Austria, Wales, and other UK universities as well, and an international science team with 9 different countries involved. So a very international team, but it's led by the UK. So that's Pancam, and I'll go into more detail about that later. We also have an infrared spectrometer, so that looks at one of our pixels and goes further deeper into the infrared to help with looking at mineralogy. There's Wisdom, which is a subsurface sounding radar. So this is a little bit like the instrument on Mars Express, except that it's on the surface now. There's Adron, which will be looking at neutrons on the surface as well, and again looking for hydrogen just underneath the surface. So the way that works is by looking at cosmic rays coming in, or at least looking at the neutrons which come out having if cosmic rays hit the surface. And so from that you can tell, from the energy of the neutrons, you can tell when you have a water atom in a molecule, and so looking at H2O, okay, that's what it's looking for, water. So there is also CLUPI, which is a close-up imager. So this is like a geologist hand lens, So these ones on the left are the so-called context instruments. And actually today and yesterday we were involved in a simulation of the mission associated with these parts of the payload, and so doing a end-to-end test with the operations center, which is in Italy, about how these are working together, and that went pretty well. In the middle here, there's the drill. I mentioned this is drilling 2 meters down underneath the surface. There is also a little instrument in the drill tip, which is a visible and infrared spectrometer. So that does the geology in situ underneath the surface. So we have the geological context from Pancam and ICEM, and then making the link with looking what's happening underneath the surface. That's a tiny spectrometer inside the tip of the actual drill. So what that drill does is get a sample, puts it into the analytical drawer of the rover, and then the analytical drawer instruments actually look at that in detail. So there are 3 instruments there. So there's micrometer, which is a visible infrared spectrometer, the Raman spectrometer, which has involvement from the UK in it. Leicester University are involved with that. So there's good academic involvement in the rover in the UK, and then the MOMA, the Mars Organics Mass Analyzer. So this is the thing which will analyze the samples and look for things like carbonates. It will also look for something called chirality. So this is to do with left-handed and right-handed molecules. So one of those is used by life and one isn't. And so that's one of the ways we can tell about whether things are biomarkers or not. So it's a very sensitive and collaborative and comprehensive payload for looking at the samples. And of course, Pancam will get the images, so that's very exciting. So this is a little video about the rover. I'll start that in a moment. So we're looking for life on Mars. Our launch is 21st of September next year. It lands on the 10th of June 2023. So that's the date for the diaries in a couple of years' time, 10th of June. It will drill up to 2 meters underneath the surface of Mars, and we have context, as I said, and analytical instruments to do that. So the rover, this is a little video about the rover just before I start that. So here's the mast. As I say, Pancam sits about 2 meters above the surface. Here's the drill on the front. Here's the wheels. Here's the solar panels. That is the analytical drawer on the front. The rover itself was built in Stevenage, in Airbus in Stevenage. The whole industrial contract is with Thales Alenia in Italy. They're running the whole mission, but actually it was Airbus in Stevenage which built the rover. And so this is an artist's impression or a computer animation of what the rover is like. So as it turns round, we can see the solar panels here. Pancam's following us because it can go all the way around. These are the antennas associated with Wisdom on the back here. The wheels, of course. This is the drill. And then the drill moves upwards like that, having got its sample. It's a drill core sample, which it then puts into this analytical drawer at the front for analysis. And so Pancam is watching that all the time. We can see that with our high resolution camera. There's also the Kloopy is on the drill here, so we can see that as well. So a very comprehensive payload, and that's the way it works. And as I say, big industrial involvement in the UK, as well as the academic involvement from ourselves and our partner universities. So, but UCL Mullard Space Science Lab, we're the lead of the camera system and working with other institutes in the UK. On the front, you can just about see the calibration target for our cameras. This was built by Aberystwyth University. So there's a couple of fiducial markers on the rover as well, which are also Aberystwyth. So that's the other hardware team in the UK, but that doesn't have any electronic stuff going. So in the top here in the optical bench, we have the cameras, and that's where the electrical stuff goes on, and that's where we take the images. Okay, so that's the rover. Okay, and just to give you an idea of size, this is a model of the rover. So this is the last time we could get together as a science team, the science working team of ESA at the European Space Technology Centre back in December 2019. So since then, we've had another meeting, of course, via Zoom, a bit like this one meeting, but last time we were able to get together. This gives you an idea of size. So this is somebody who's just over 6 foot, last time I measured, and just gives you an idea of size of the rover. Okay, so why is it called Rosalind Franklin? So this is after this person. So Rosalind Franklin was a brilliant X-ray crystallographer, and she took this famous image called Photo 51 of a fiber of DNA. So this was critical to Watson and Crick's discovery of the double helix. They got the Nobel Prize for it, but it's her work which went into it, which was very important. So, so our rover is named after her. She also did very important work on the structure of carbon and indeed of viruses. So very topical, of course, at the moment. But Rosalind Franklin, the rover, is named after in honour of this person. So, and I should say the UK Space Agency had a competition for people to suggest names of the rover. So of course we got the usual Rover McRover face, things like that, people suggesting, but also much more sensible names and really well-deserved names such as Rosalind Franklin. So that's the one which was chosen from about 36,000 entries. So, really exciting. The public got really excited about that. Okay, so why do we have to drill? So we need to get underneath the very harsh surface of Mars. I mentioned the temperature is harsh, but also we need to get underneath where ultraviolet radiation can get to. I mentioned ultraviolet bathes the surface of Mars. It's like being under an ozone hole all the time. We also need to get below oxidants underneath the surface here, about 1 meter. And then underneath where ionizing radiation can get to, about 1.5 meters. As I said, with my student a few years ago, we discovered that was the case. And so fortunately, the rover had been designed for that. Okay, so the landing site is very exciting. So that's Oxyoplanum. So that's in the mid-latitude regions of Mars. We have to choose mid-latitudes because we're a solar panel-powered rover. We need the solar panels to charge the batteries so that the batteries can drive heaters to keep the rover warm at night in that really cold temperature. So we need to land near the equator. Also, we're near this dichotomy boundary between the north and south regions, with the low terrain here and the higher terrain in the southern hemisphere. As I said, the much older terrain in the southern hemisphere. So in this sort of region, and these are the landing ellipses associated with the 2021 launch, 2022 launch. And so this is Oxyoplanum. So it's clay-bearing rocks in this location. We had an exercise over last summer to map this out in great detail using the best geological maps available from the various instruments on orbiters at Mars. And it was already known that there's a remnants of a fan or delta near the outlet of Cocoon Vallis, which is in this region, and so this delta remnant is here as well. So this is a very interesting site. It's a little bit away from where Perseverance is landing, which is over here somewhere, but nevertheless that's still near the dichotomy boundary and an interesting location. They're in Jezero crater. Okay, so a bit more about Pancam. So Pancam is the science eyes of the Rosalind Franklin rover. And so we have, in this, we have filter wheels in front of the wide angle cameras. So the two wide angle cameras are spaced apart 50 centimeters. So if you can see me with my video on, you can probably see this. So this is a model of the camera system. So this gives you an idea of the size of it. So these two eyes are 50 centimeters apart. So that gives us really good stereo vision. This is the high resolution camera. And so that gives you an idea of where that is. And so we have 3 cameras, the science eyes of the rover working together. So in front of each of the wide angle cameras, we have a filter wheel. So that's shown here. The high resolution camera is here. So this is where the light goes in. There's a mirror here to deflect the light, a focusing mechanism, and then the image plane is there. So this behaves a little bit like a telescope. So we're looking in great detail at rocks. The Pancam interface unit, some electronics and the DC-DC converter. So these are electronics housed all within the optical bench. So this optical bench is what houses the cameras. This is what sits on the top of the mast. That's the model which I showed you. And then in addition, we have the so-called small items, which are the Pancam calibration target, which sits on the front here, fiducial markers, And we have even a rover inspection mirror, so we can actually look with PanCam underneath the rover using a mirror, so that's quite good. So with this, we can get stereo from the two wide-angle cameras, we can get colors from the filters, and also the high-resolution camera is a color camera. And then we get shapes and scales. So the shapes from the fiducial markers and scales from those as well. So this is who did what. And so our lab, MSSL, we built the filter wheels, the PIU, the DC-DC converter, and the optical bench. So our partners in Thales in Switzerland built the wide-angle cameras themselves, the high-resolution camera from DLR in Berlin, and OHB in Munich. Aberystwyth University, the calibration target, fiducial markers, and the rover inspection mirror. As I say, our science team is international. So here's a couple of images. This is the team just before delivery of the camera system. The camera is in the back of the car here on the way to go around the M25 from us in near Dorking in the lab round to Stevenage for the delivery. So these are some of the key management and engineering people who were working on the camera at the time, and basically were responsible for the delivery of the camera. Here's a science team meeting. So a couple of years ago now, nearly, we had a science team meeting. That's the last. Let's see. No, we had one in 2020. So this is the last but one meeting that we had in person. So the last couple of meetings have been remote, of course. And we have meetings, every month, every couple of weeks, and so on to keep the team together and keep it working. Okay, so the filters. This is an exciting picture to show. This is the actual filters on PanCam, the wide angles cameras. So these are the things which will allow us to do the science. So we have 11 filters on each of the wide angle cameras. So we can see the wavelengths and the widths of these at the top here. So this is R, G, and B, red, green, and blue. So we can get color images with that. These are the geology filters, narrow but not very narrow, and then the solar filters, which are very narrow filters. And so with that, we have one of these at an absorption signature associated with water, so we can actually measure water on the surface of from the surface of Mars in the atmosphere. So I have another PhD student working with me at the moment on that. So she is going to be looking at inverting those into column densities and then height profiles of the water vapor in the atmosphere. And the color high resolution camera also provides rock texture. So it's a very powerful camera system, extremely powerful. The errors associated with these particular wavelengths mean that we have very good identification of water-rich minerals like clays, the best we can possibly do with a visible camera. So it's a very good camera system. Okay, here's a couple of other views of the camera system. So this one is a blow-up picture showing the filter wheels here. This is what it might look like on the surface of Mars. So this again is a 3D rendering by our colleague Helen Miles in Aberystwyth, who was doing this. So here's PanCam at the top. These actually are navigation cameras. So these are more like human eye spacing. This one is the infrared spectrometer. So that looks at one of the pixels of the high resolution camera. And so that is very tightly aligned to that. And in fact, we've done calibration tests to make sure those are well aligned. Okay, PamCam has been used in the field quite a lot. We've done a lot of tests. So this is an emulator, again, built by Aberystwyth, which has been taken all over the world to look at particular features. This 3D model, I think, is from one of the trials in the Atacama desert in Chile, where we were looking at some of the geology here. So you can look, is there any geologists in the audience? You can look at dip and strike. So this is looking at sedimentology, how things link up together. We can also look at composition by looking at the ratios of the colors. So this is principal component analysis using, stretches of the data using the filters to actually see things like gypsum, sulfur, etc., to get the composition of the rocks. And so that was done, this one from a field test in Iceland. The Utah desert has been to. So in 2016, we had a trial, again, to prepare people for operations, really, in the Utah desert. So with a remote rover involving a time difference, and then the operation center back in Harwell in the UK, in the Midlands, and so near to Oxford, just a bit south of Oxford. And so I was one of the ones in Oxford, didn't get to go to the Utah desert, sadly, but there we go. And so we had a paper about this a couple of years ago. Again, another trial in the Atacama desert here. So this is the type of image you get. So just off to the right here was a truck. You can't see it, but of course we know it's not Mars because of that, and also the fact the sky is blue. And the wide-angle camera, this is the spectra which you get from the particular features. Okay, again, another 3D image. Okay, so I'll just show you this little bit of video about the landing sequence, just to illustrate how we're going to land. So it has heat tiles on the front to stop it burning up in the thin atmosphere. Parachutes, which we'd have had a bit of trouble with, but those come out to slow the thing down towards the time we can release the back. Then we rely on the landed platform, which has retro rockets on it, which you can see those working there to make the thing hover before landing on the surface. Okay, so then we open the solar panels up. This all happens over a matter of days. You know, this is very much speeded up compared to what the reality is. But of course we need solar panels for power for that first night. Deploy the instruments. So Pancam is the first instrument to be deployed. That's at the top of the mast here. And again with the other camera systems which I mentioned. So we survey the surface, see where to drive off and to go and start looking. And again, this is very much speeded up, but it shows you the idea of driving down the ramps onto the surface of Mars. So we have something called wheel walking, which you can see a bit of that going on. So that is to, if there are rocks in the vicinity, we can effectively walk over those. So having decided a location, we eventually drill. So here's the drill being deployed. Drill's 2 meters. As I say, this is very much speeded up. Our real mission lasts about 6 months. We're expecting a few of these drill sequences. So the sample goes into the analytical drawer and then is pulled into the inside of the rover, which this cut is to. So the samples are then distributed to the instruments. So this gives you an idea of what's happening inside the rover. Okay, so time's running on, so I'll sort of go to the next slide, oops, hopefully, which can then tell us. Okay, so this is Pancam being integrated at our lab. So this is one of my colleagues on the engineering side, putting Pancam together. Here is the filter wheels and the filters ready to go into it. This is some of the electronics going in. Everybody, of course, has to be very clean. We have planetary protection, strict planetary protection in progress. We also have to be careful about electrostatic shocks. And so that's something, you know, which could potentially damage the electronics. All this is put together very carefully in very clean conditions. That's the inside of Pancam. And so you can see the wide angle cameras here, the filter wheels at the front. This is the electronics, some of the electronics here, and the mirror associated with the high resolution camera, the focusing mechanism, and the image plane. Okay, so this was delivered to Airbus in May 2019. Here's the proud team which have been closely involved with this. with Pancam in the box ready to go in the car. These are some of the filters, actually. These are the flight filters having arrived from the manufacturer. This is before they were installed. So this is a year or two before that. So they're in boxes which look a bit like contact lenses. And actually ESA did a press release about that, showing this image as one of their images of the day in 2019, around about our time of delivery. And made the analogy with contact lenses. So it's like putting a lens in front of the eye with a particular color in order that we can see the surface in particular wavelengths. And so that gets the idea across. Okay, and I'm so proud to be able to show this. This is Pancam on the rover itself. This is the rover undergoing some tests. Actually, these ones were in Toulouse in one of the aerospace facilities there just before the thermal vacuum test. And so there's the rover, Pancam at the top of the mast, so the optical bench. This is the real flight model, the one which is actually going to Mars. And that is, of course, is on the top of the mast there. Our fiducial markers, our calibration target, our rover inspection mirror, and where those are on the rover. So this is amazing image. Okay, and that's the installation of the mast. So this was a very proud day for us in August 2019 when we got the camera on the rover for the first time and got images successfully through the system. So this is my colleague Matt Gunn from Aberystwyth actually holding up a piece of paper here. And this is the image from Pancam. It says, "Hello Mars." Okay, so it's our first light image on the rover in August 2019. Recently, we've done some tests which show it's working well. It's now back in Turin, actually, for some further tests before it goes off to the Baikonur Cosmodrome later, well, early next year is when it goes. Okay, so coming towards the end now. So the this is shows the journey. So the ExoMars 2022 journey from Earth to Mars. So the launch, 20th of September Russian time, but European time, that's 21st of September. So we and 1410 UTC. It will travel a total of 569 million kilometers to get to Mars. You have opportunities every 2 years to launch to Mars. We missed this one because of problems with the parachutes and some other technical issues, but we're going in 2022. So September next year is when we launch. And that gives you an idea. I'll just show this little video as well, which is quite nice and shows some of my colleagues involved in the engineering side as well. See if I can run it. Oops. Right, here we go.
Pancam is a panoramic camera. Yeah, that's what it stands for.
Pancam, this is the scientific eyes of the Rosalind Franklin rover. So we're looking at the scene on Mars, trying to do some geology, trying to do some atmospheric science.
The instrument is a fairly plain white box, essentially, but it's what's inside the box that's interesting.
We've packed as much science as we possibly can into what is basically a camera system.
We have 2 wide field cameras on the ends.
Stereo imaging cameras of the wax, one at each end. So on a stereo baseline of about 500 millimeters for stereo imaging and plotting of routes on the Martian surface. So looking at what's in front of the rover and working out where it could go.
So each of these wide-angle cameras has a filter wheel in front of it with 11 positions. And we can move that around to look at the different colors of the light coming from the surface of Mars. And so with that, we're able to not only build up a color picture, but also to look at composition of the rocks, in particular looking at the light which is reflected from the rocks, to look at the minerals in them, and to look particularly for water-rich minerals, because of course we're looking for water and life on Mars.
And then we have a high-resolution camera.
So the HRC light path comes in, goes, hits a fold mirror, goes through a focusing mechanism in this area, and then projects onto a sensor down at this end.
This will enable us to actually see fine-scale, small-scale details on the Martian surface. For example, texture on rocks, or it will enable us to see single grains on the soil, and that's very important for the geological investigation of the surface.
We were PIs on the optical bench, and we produced the PIU and DC-DC converter, and they were built here.
we already delivered the hardware, so it is now in still finish in Airbus. Now they're putting all the things on the rover. The project starts since 2004. So we're talking about this 15 years of our life is working on it.
I remember the first time I saw part of Pancam and then got to handle some of it. And it was a pretty amazing experience to think that, you know, things that you've touched and helped with will hopefully be on Mars soon.
It would be a fantastic discovery to actually be able to find evidence for life anywhere else on the universe, and Mars is the nearest place we can look, and so our rover mission is specifically designed to do that. Okay, so just a couple of recent images of things to do with the rover. So on the left-hand side, this is something called the ground test model, which is in Turin. So this we're going to use during the mission, actually in a Mars yard. So it's a sort of big sand pit with rocks, and with that we're going to be able to simulate what is happening on the surface of Mars. That's near the operations center, which is just next door to this Tarlasolenia, Italy. It's a place called Altec, and so that's where we'll be doing the controlling from. But of course, we may be doing it remotely. It depends what happens with the pandemic. Today's trial, for example, was remote. It wasn't using the ground test model, but we were working together as a team. So the flight model of the rover. So this is the actual one going to Mars. So this is shown in Cannes, where it was until just March this year for some additional tests. And so this is it on the Kazachok platform. So all of this is flight, what's going to Mars, and again Tarlasolenia Space the lead for that. And you can see Pancam in its folded up position. So this is in its launch configuration, ready to be integrated with the rest of the spacecraft. So it has now gone back to Turin, as I say, for some further tests. So just finally, we're also involved in the Mastcam-Z team on the Perseverance rover as well. So this is very exciting. At the moment, Perseverance is about to launch the Ingenuity helicopter just in a few days' time, hopefully. I think the earliest it could happen is the 8th of April. So Mastcam-Z, which is the camera system there, which we were invited to help with, and you know, basically provide some advice each way associated with camera systems for Mars. So that will be able to take images and also videos of the little helicopter as it ascends, hopefully in a few days' time. So very exciting. And of course, this mission is looking for life as well. And it will collect samples in particular ready for bringing back later on. So just finally, so the Rosalind Franklin ExoMars 2022 rover will provide an important new dimension on Mars, drilling underneath the surface. And our Pancam with the other context instruments provide geological and atmospheric context. Okay, so I'll stop there, having gone well over an hour. Sorry about that, and see if you've got any questions.
Okay, thank you very much, Andrew. It was excellent, all that. As usual, if you've got any questions, can you raise your hand and wave? And I'll try and spot you.
Actually, I can see someone called Catherine has got a question.
Yes, Catherine's got a hand up. Catherine?
Okay, do you have a duplicate rover in case the original one goes wrong, and then you can try to work out what the problems are? I know that NASA does things like that.
Well, we have this ground test model, which will be on the ground, and so we can test sequences on that. So that we will have in Turin. It's not a flight rover or anything like that, but we do have for Pancam, we have a flight spare of Pancam, so we have that in the lab, and that actually is in the clean room at the moment. Is all ready to take commands and so on. So we have that to work with. We also have another version of Pancam called a life test model. And so that we'll be able to exercise as well with commands and so on. So, yeah.
Thank you.
But not a full rover, yeah.
Anybody else with any questions? Wave. Andy Davey.
First comment, Andrew. Best presentation I've ever seen by far.
Oh, well, thank you very much.
Yeah.
Gosh, that's embarrassing, Bo. Thank you.
No, my question is, have you calculated the number of man hours that you've put into it all? Because it's an absolutely enormous effort.
It is, and of course, you know, it's a big team effort. So I should say, I mean, there's a big engineering team which has worked on this at the lab, and also at other labs as well. You know, in Germany and in Switzerland, and in Aberystwyth. So all of these people have worked together a lot. I personally started working on this in 2003. We actually did the first proposal for Pancam before Mars Express and Beagle had actually launched. And so, you know, we were already anticipating the next mission. We hoped it would be sooner than this, but nevertheless, you know, we take what we're given, and you know, it takes a while to develop these things. And yes, there's a lot of man hours and a lot of cost has gone into it, but it's worth doing. It's still internationally at the cutting edge of what's being done. So Perseverance, which is on the surface of Mars at the moment, that can drill 6 centimeters and can get drill cores up to 6 centimeters. We're doing 2 meters, you know, so it's much deeper than we can go with other spacecraft, and so ours really still has a very important place, and the Chinese are not going to do that with their rover either. So so it's definitely still worth doing. We had, during the program, we had a couple of program changes. So initially it was going to be a European Space Agency mission only. Then it was going to be European Space Agency and NASA. In fact, at one point we were going to be landing on a sky crane, the thing that Perseverance landed on, and there was even the possibility of there being 2 rovers dangling from this at one point. For those of you that saw the sky crane images from and videos from Perseverance, that's amazing, you know, to do it with 1. But imagine doing that with 2 and the sort of difficulties associated with that. So they decided to not do that, too engineeringly difficult, and decided not to go that direction. So so unfortunately NASA pulled out, and actually it was lack of funds which caused that thing to change. And so then we worked with Russia, and we're still working with Russia. So in today's simulation, you know, there are people from all around Europe and from Russia involved in this simulation. So so very exciting, but also a very tiring day.
I've actually got a second part, because I'm a mining engineer.
Oh yeah.
So I'm very interested in the drilling that you're using.
Yeah.
What type of drill tip? Because you said you got sensors in there, and obviously you've got a system for clearing the chippings away so you can go in. But presumably the sensor will tell you if you hit something that's very hard to abort.
Well, the sensors are in the rover itself. And I don't honestly know very much about the drilling system in detail. I mean, the sensor which I mentioned actually is a camera, and you know, visible and infrared camera for looking at the geology down at the bottom of the drill thing. But yes, we drill down, get a core, and then bring that up onto the surface. But yes, you would know much more than me about that. So I don't know the technical details of it, I have to say. Sorry.
Okay, thank you.
Yeah.
Catherine, you've got another question?
I've always got questions. Yes, I was looking at the specification of your high resolution camera. And from my point of view, it isn't really that high resolution. It's only 1024 by 1024 with a 10-bit ADC. Were you limited by getting a radiation hardened one, or was it bandwidth or space to fit it into the Pancam?
Yes, getting radiation hard things. You know, at the time we were designing it, that was the best we could do. Yes. Now the one which is, and actually though resolution we will be doing as well as the NASA rovers. So they have bigger sensors, but the field of view is different. So we actually, if you look at the instantaneous field of view of what we have with the HRC, that is actually very competitive when we're down to sort of 10 microns type of.
Okay.
Type of thing. So you know, what matters is not necessarily because you know, nowadays, well, what 25 megapixel chips easily in domestic cameras, but
Yes,
and smartphones 12 megabits or whatever. But yeah, for space stuff, we have to use what we can use at the time we're designing it, and so that limits you. Also, performance-wise, we want to have the best we can. But resolution-wise, in terms of what we're getting with the science, it is enough for what we want to do. So we have, a science traceability matrix which traces out exactly the science we want to do and the resolution we need to do it with. So this will definitely do the job.
Thank you.
Anybody else? Wave a hand. Tony Morris.
Hi, Andrew.
Hi.
When you're mapping the surface with the colour filters, how are the colour filters calibrated to indicate the different minerals?
Well, we have an onboard calibration target, so that is coloured different colours which we know very well what they are on Earth. We've also looked at the transmission spectrum of each of the filters to get the exact wavelengths that the filters are will allow through, and of course I've looked in detail at the calibration target colours. Of course, we get dust settling on that, and so we have to take account of that and take account of the dust in the atmosphere and so on as well. So all of that is quite a complicated thing, but it's been done before on the NASA rovers, and we, as I say, we're involved with them on the current one. So we understand the types of things which are needed to do, and so we will be doing that as part of our calibration process. So yeah, getting the colours right, the calibration target is playing a big role in that.
Okay, thank you.
Anyone else? Andy Davey again.
Yeah, just one quick one. Obviously, there's a lot of preparation work. Once you achieve successful launch, you've then got a significant wait to landing. Do you all get a well-deserved rest?
No, unfortunately, I'm sure there will be a lot more simulations and things like that to make sure we're all ready. But there will be a bit of rest, of course, for the team. But I'm sure it will give us time to work on other projects as well. So there's also things like teaching to fit in and all that. So although I think I will get a bit of a break with teaching for this mission, so I'm looking forward to that actually.
Okay, thank you.
But I enjoy teaching, but actually doing it all at the same time is quite tricky.
Yeah.
Catherine, you have another question?
Yes. There's a puzzle at the moment on Mars over the seasonal concentrations of methane and oxygen.
Yeah.
Will your rover help to solve those problems?
Not very much. I mean, the trace gas orbiter was sent to look at that in detail, but of course it can only look from orbit, so it can't really get the stuff near the ground. I mean, the combination of Curiosity and Perseverance, and I mean, I think we can take gas samples actually with the MoMA, and so we will probably be able to contribute to it, but it's not what the mission is for. The mission really is for drilling underneath the surface to look for signs of life and analysing the samples which we get from underneath the surface. So that's the main focus, but yes, there's other things we want to do too. And, if we can contribute to that, that will certainly be something which is important. Because as I said, it is definitely a puzzle at the moment of what has happened with that methane. So it's an interesting question. Yeah, thanks.
Thank you.
Right, I think we've worn our guest speaker out. Lots of questions. It's been an excellent talk. Thoroughly enjoyed it. It's nice, as somebody commented in the chat, it's actually nice to see somebody who is actually directly involved in these missions to actually talk about what's going on and how things are put together. So can we all show our appreciations to Andrew in our normal way?
Thank you very much. Okay, thank you very much.
Thank you very, very much.
Okay, cheers. Yeah.